list some examples from last time, and let me mention a couple of the results concerning the previous lemma. I guess it could be a combination of lemma definition 2, so 3 plus 5. This is a combination of lemma point. Well, I forget the labeling in the book. What is that labeling? 15, 16, 17. So the first part is what do I have? So if and then will belong to the set collection highlights, and then some of them have to be belong to. I guess maybe let me just. So moving on to our next. Then part 2. So what is the part 2? So if P is positive, then it is immediately implying that the period is equal. And then the last piece, which is a little bit tricky, using a number theory. If the period of x is equal to 1, then there will exist an index and capital N. Of course, that index N will depend on x. So next index N is just that for all steps starting from N, P is actually guaranteed to be positive. So I'm not going to walk through these results. They are in the book, and so you could just read the book for the proof. The last thing that I want to say is number 6, which is. If this one is more important. So if I could have x communicating with y and the y communicating with x, then I'm gonna have then it must have the same period. So I'm going to make use of, the results number 1 here to prove this lemma. As usual, I would just start with the definition of being communicating. So x going to y, finite time, implying that exists. Say index, we multiply and internal, just that p and internal x, y is positive. Similarly, y equal to x, implying there exists a index times step and internal So basically here I will try to prove one guy is less than the other, and reversely. So I want to show, so I guess allow me to denote this as CX and CY, so I don't have to write this all over again. So let's say, so denote CX being period of X, CY being period of Y. So I want to show, so one direction is CX is always less than CY. Right? And the other direction is, well, by interchanging the role of X and Y, I have CY less than C. And if they both hold at the same time, then they have to be equal. Alright, so that is the idea of the argument. And of course, if I can show this to hold, then by just switching the role X and Y, this would just follow exactly the same thing. So one direction is enough to write down the arguments for one direction. So what kind of, so how do I know CX less than CY? So actually okay, so now proof of CX less than CY. Alright. So the idea here is, alright, so what is CX? So CX will have to divide all K for all K inside of IY. Alright. Alright, just in case, well, this is the notation for divide. Suppose I have CX divides every element K in the IY. What does that say about the CY? So that would imply that by definition of period, Y is CY, which is the greatest common divisor of the IY. Right? Because CY is the greatest common divisor of IY, and I have a CX divides everything in IY, and so CX has to be supposed to be less than 0. Right, yeah. Greatest common divisor, the largest number that divides everything in IY. That is the definition of CY. And if the guy CX similarly divides everything in IY, then the CX should be less than 0. Right? Because this is the largest number dividing all K in IY. Right? By definition, this CY is the largest number. And if I already show CX here also divides every K in IY. So CX must be less than CY. Right? Yeah. So basically this comes down to this goal right here. It comes down to that. Alright, so what can I say about the n twiddle and the n little n twiddle? So the first thing I can say is step 1. I can say about not that have an m twiddle plus n twiddle x-axis. This is always valid from below because I have a path going from x to y in n twiddle number of steps. And then from y going to x in an internal number of steps, and this is positive. In particular, that does imply what? That does imply n total plus n total we know to x. As a by past product, that also implies Cx here, period of x. This divides n total plus n total. Yeah. So that is the step number one. So step two. Now we're going to consider for every element k in this set, I1. So now for all k in I1. Remember this again. This what is this I1? This is the collection of and such that Pn little y1 is positive. Alright, considering every element in this collection. Okay, what can I say about P and fiddle plus K plus n fiddle? What can I say about that probability? Can we go from x to x in that number of steps? Is it possible? How's that?
You first go into the steps to y,
Right, so n fiddle
x, y,
Y.
times p, k, y, y,
p k y y
times p into the yx.
y x. Yeah, so that is a possibility. And of course, that will have to be strictly positive for sure. So that does imply. Let me erase this piece. So what does that tell me? That tells me that n total plus k plus n total n total plus k plus n total also belongs to Ix, by definition of Ix. Again, as a byproduct of this property, I have this little Cx must divide this number, and zero plus, maybe allow me to divide in order. Yeah. So, what do I have so far? Step number one, I have Cx dividing n total plus n total. This is step number one. This is step number one. Right? Then this is step number two. So, what is the conclusion now?
CX divides K.
Right. So step three, well, I guess that's step one plus step two. Cx must divide little k. Do we have to explain that? And which is basically done. You know what that? You know what that is? A what?
A brief explanation.
A brief fact.
Yeah, just to explain it real quick.
You want me to go over?
Yeah.
So, well, I guess that's just property of the of integers, I guess. So if C divides A and C divides B, then C must divide the sum, maybe the difference. All right. This is because, well, I guess this is because C divides A means A can be written as a product of C multiplied by number n. Similarly, C divides B, equivalent to B can be written as C times a integer n. So if I take the difference, let's say B greater than A, let's say. So B minus A is just, well, I have a common factor of C and, yeah, okay. So anyway, so this is done. Basically up to this point, we already have Cx divides every k 9y. By definition of the largest number dividing every k 9y, Cx is less than C. And now, if they want to show the other direction, I'll just switch the role between x and y, and rewriting the same proof basically. All right, so let me move on to the next, the most important piece of the whole chapter, and I would say the most important piece of the whole book, the so-called limit theorems of part 2. Limit theorems. So in order to do this, 3, 4, 5, 6. So I need definition. 7. So a function here, this is generalization of the stationary distribution. Let me call the function denoted by mu, which is a map from my state space, mapped to this half interval 0 to infinity is called a stationary measure. Put the measure in quotes. It's called a stationary measure if of course, not every element is identically 0, so I need to have at least one mu as being positive for at least one x in the state space. Of course, I will not consider the case where they are identically 0. That is just trivial, so I don't care. At least one of the element x must have mu as being positive. Then the second piece is the equality. Entity mu multiplied with p is second. Right. So pretty much it satisfies the condition of being a stationary distribution. However, the sum need not be equal to 1. So just let me write down the definition, and then let me put the remark here. Is a stationary distribution. I denote that as the delta pi is basically a specific, say specific, example of a stationary measure. With the further condition on being distribution, the further condition that the summation of the pi x is identically equal to 1 for R over S. Right? So pi, a stationary distribution, is simply, according to the definition over here, that is just a stationary measure with the restricted condition that the sum is 1, because it is probability distribution. Right? In general, of course, in general, a stationary measure need not have the sum being finite. So in general, the summation of the mu x in S may be infinite, right? In general, may be infinite. To be called a stationary measure. Okay. Part 2. However, if my state space, well, if my state space is infinite, I cannot say anything much. But if my S here is finite, S is finite, then a stationary measure of mu can be normalized to a stationary distribution by the relation, say, so I just denote pi of x to be just mu of x over the summation of the mu z or z in x. Alright. Yeah, right? If that space is finite, then suppose I have a stationary measure according to definition 7, then I just take a sum, take mu x divided by the sum. Then the pi x down is a distribution, of course, because now the sum of pi x will be 1. And it is stationary. But in general, we cannot do that. In general, it is a hard problem. Because in general, the sum of the mu should be infinite. Alright. So let me move on to now let me move on to the limit theorems. Prepare for that. Let me just give some notation. I denote by I standing for irreducibility. I denote by R standing for recurrent. What else? Maybe let me write it up here. Yeah, that's just a notation. So let me write up here so that I can have it and trace back. Let me write it here again. Sorry. So I stands for irreducibility. R stands for recurrent. exists a stationary distribution. Stationary distribution pi. So in the book, they only use the capital S, which could be confusing with the state space. So I use the S of pi to denote that I have a distribution pi on the state space and it is stationary. All right. What else? So A is a periodic signal. Okay. And what else did I need? I guess I want to n sub n little y is the number of times visiting y up to the steps n. Alright. So n, capital N, sub n. Alright. The number of times visiting state y up to step n. Alright. Start with this. I guess let me write this up here. Now let's move on to the theorem. This is a combination of a whole bunch of results from 119 up to how many of them? 23, I believe. This is the theorem. So what can I say? Okay. So the first thing is if the Markov chain satisfies the condition I, and I know it has a stationary distribution pi, the conclusion is that I have this pi y here must be equal to exactly 1 over expected value of y and t y. Alright. So, okay. So if I know that the chain is irreducible, and I know it has a stationary distribution, pi, then the pi is given by that formula. As a consequence, that pi is unique because it must be given by that number, and that number is the one and only one. So as a consequence, pi is unique. In other words, if I have, say, another stationary distribution, then they have to be the same. The next one is if I have I plus s pi, then plus the aperiodicity. The conclusion now is for all x and y, I have a p and x y. How to converge to y. Recalling that is 1 over t1. So that means if I further have a periodicity or periods, they are equal to 1, then p and x y. The limit as n going to infinity must convert to that I1. Okay. So that is the second part. The third piece is suppose I plus s pi, and then plus a function f from s to r, just that summation of f z, pi z being infinite, in s. So this series converges absolutely. Okay, suppose I have irreducibility, a distance of a pi stationary distribution, and suppose I have a function f satisfying this condition. So basically this can be thought as the integration of f against pi. This series converges absolutely, then I would have the average, so 1 over n, summation of f of xk, k from 1 to n. This will converge to the summation of fz pi z, say z and s. This will hold with probability. Let me stop for a moment and mention this limit result. And you can think about this as being, so this is what they usually call a so-called Kirchhoff quadratic theorem. So this is something just for fun here, so you need to remember this. So this is called the so-called Kirchhoff quadratic theorem. All right, that data right here. All right. So what does it do in reality? So in reality, suppose the chain is irreducible and I know it has a unique stationary distribution. But in reality, it's very hard in order to know the explicit expression for the pi. It's very hard to know. Because in reality, you may have infinite state space. But doing some math, you know it's irreducible, you know it's unique. Then, what can I say about the pi? For instance, so pi is not known explicitly, like you don't know this. You don't know that in reality. However, you can say something about pi, which is typically enough for the analysis. For instance, you can just test, however, say second moment, might be known via that limit theorem. That means 1 over n summation of xn squared will go to summation of z squared pi z, which is the second moment of pi, right? That is the second moment, for instance. So what do I do in say I have a modeling for a Markov chain? I'm going to plug this into the computer. I'm going to plug this into the computer. I'm going to run the chain. So this is chain of that. I'm going to run the chain for a large number of n. I compute this sum. If this sum always converges to some number, as I observe a numerically number, then I know that has to be the second moment of pi. If that makes sense. Yes?
Oh, and also the g times pi g is d.
The what?
Just what is the product of the g and the pi g?
What is the product z squared summation?
Yeah.
That is the second moment of the distribution. And to think about, I guess, I mean, how do you compute, say, if pi is geometric, let's say. See, how do you compute the second moment of the geometric? Want to do x k squared pi k for 1 infinity? Isn't that how you compute the second moment? Yeah.
That's easy.
So here, z here is a state in this. On the other hand, suppose I run this for many times. I compute this average. And somehow they don't convert to the same thing, then I know the pi here does not have a second moment. Or pi may not be unique, for instance. Because if pi is not unique, then this may not hold, for instance. So that's what they do in the yes.
What do you mean by with probability 1?
That means, yes. So I guess the probability of this event is equal to 1. Yes.
Can you explain how uniqueness even matters? Like why they might not converge if it's not unique?
If pi is not unique,
Yeah.
then then you may run the chain for some time. This may have different limit. It may have different limit. So for instance, when you plug this into the computer,
Yeah.
you start the chain for one time, you compute the limit here. Then you start the chain all over again, you do the numerically computing of this. It may give you another number as for very long n. And so that indicates either the pi is not unique or the pi doesn't have a second moment. Think about it, Cauchy distribution, for instance.
I see.
Yeah.
But if you know like I plus s pi, then should there always exist like a unique pi?
Yes.
Oh,
So that comes from the first result here. I plus s pi, then the pi is unique. Yeah. Sure. Remember that this event here only holds the probability 1 if I know this function is integrable, being integrable with respect to pi. Think about it. Alright. And so in reality, say, do I know the second moment? Just run the computer. Let the computer run. If it has a limit, then it should be the second moment. But say, what if you don't care about the second moment? Let's say, suppose you be in way 2 bit e to the x, for instance. It may not have an exponential moment, may not. So that may not go anywhere. May not go anywhere with the exponential moment, for instance. And so it has to go with the condition that f is integrable with respect to pi. So, that is the P concerning the existence of a stationary distribution. Let me move on to if I plus recurrent. Suppose if I only know this in general, then with probability 1 and y over n will converge to 1 over expected value of y as n goes to infinity. This event holds with probability 1, regardless of the initial state. So these limits here does not they don't say anything about the initial state x 0. That means I can start from anywhere in the state space, and eventually I will have to converge. All right. And the last piece is what? What is so the last piece is have again I plus recover, then there must exist a stationary measure mu such that 0 less than mu 1 less than infinity for all y yes. The formula of mu 1 can be found in the theorem, I believe, that is from Penn. Okay. So note that this theorem doesn't say anything about the stationary distribution. In other words, mu of z or level z may be infinite, so it cannot be normalizable. Right? Do not confuse this with the S pi over there. The S pi over there saying I have a stationary distribution. But this says under these two conditions, there gotta be at least one stationary measure mu. With the caveat, sum of mu z could be infinite, but it's stationary, but the sum could be infinite. And so it wouldn't be able to be normalized to a distribution. So please do not confuse that with the S pi. Alright. Yes.
And the theory 1.20 is the I plus S pi plus A.
Oh, really? So the labeling is wrong? What?
No, I'm just asking.
No, so you're asking what?
The 1.20 is the second one.
The 1.20 is this. Just the labeling.
Okay.
Yeah, it doesn't really follow the order that I am writing here. But here I want to summarize everything in the table, so it's easier to see. Okay, so I guess, what do we mean? Well, that way. So let's open the practice. The practice number 1. From last time, so I guess I only have a couple of minutes left, and let me just mention, tell you what happens if you don't have, say, a periodic city. All right. So remember, if irreducible S pi a periodic city, all periods are equal to 1, then P and Sy has to converge to a limit pi 1. What if I don't have a periodic city? You never know anything. So the practice number 1, the problem number 1 is such an example. So practice 1. Problem number 1. Okay. So, well, I guess the first part is to compute the stationary distribution, which I'm sure you guys know what to do, right? And did anyone compute that already? Anyone? No? Really? Alright. So, I mean, you can compute. So I have a 4 states, right? So I have 4 states. 0, 1, 2, 3, and it goes like this. Is that, what was that? That's a 1, 2, 3, and the 3 go there to fill in my card. Yeah, this is the P, if I remember the diagram correctly. And so from last time, if you remember, we proved that the period of 0 is 2. That's what I did last time. Right? So that violates a periodic city. Okay? But, well, I mean, if you compute using a computer, you know for sure it must have a stationary distribution. And in fact, the pi there is actually equal to, I believe, according to this vector 0, 1, 2, 3, I believe that will be 1, 8, 3, 8, 3, 8, and 1. From my memory. I could be wrong with the numbers, but I'm sure you guys know how to find it. I'm sure. All right.
Is that, no.
Sorry?
Oh, never mind. Is that 1, 3, 8, 3, 8?
3, 8. No.
Okay.
I could be wrong, people go check. All right, I could be wrong. So this is a 0, 1, 2, 3. Okay. And is it irreducible? Is this thing, this chain irreducible? It is. From anywhere, I could go to anywhere in finite time. So I do have irreducibility, right? So I plus s pi does not plus a. Alright, so I know I have I plus s pi does not a periodic city. So actually, so what can we do? Pn 0, 0 actually does not have a limit. There is no limit as n goes to infinity. In fact, if it were a periodic, Pn 0, 0 would go to pi 0. If it were a periodic. But in this situation, you don't have a periodicity. So in fact, the Pn 0 doesn't go to any limit. And if you remember, P2n plus 1, 0, 0, what is its number? 0, right? 0 actually is equal to 0, identical to 0. In particular, it does not go to 1, 8. In particular, it does not converge to 1, 8. Obviously. Okay.
So it says 2n, you convert to 1
No, actually, 2n here, 0, 0, will convert something to over 3. Go over check. Okay. Alright. I still owe you the other problems. I guess it will be more fun and fun.